Hello, welcome to everybody. I am Dr. M.Gobi, Assistant Professor, Mechanical Engineering Department from BSN College of Engineering and Technology. Today I am going to present the topic of nanotechnology and nanomaterials. So, I will be concentrating on explaining to you the topic of nanotechnology and nanomaterials. So, the contents in nanotechnology and nanomaterials which I have chosen is basic definition, history, applications. Application in the sense applications of nanomaterials in medicine, energy, storage, industrial use, etc. And the obstacles and hurdles produced by nanomaterials development. Finally, we will see the conclusion and then the reference. So, nanotechnology, the definition of nanotechnology is that it involves the manipulation of smaller things. So, small means big. So, it's hard to imagine just how small nanotechnology is. 1 nanometer is a billionth of a meter or 10 power minus 9 of a meter. So, it is very small. 1 nanometer can also be said as 1 millionth of a millimeter. Nanoscience and nanotechnology are the study and application of extremely small things and can be used across all the other science fields such as chemistry, biology, physics, material science and engineering. Nanotechnology may be able to create many new materials and devices with a vast range of applications such as medicine, electronics, biomaterials and energy and production. So the history of nanomaterials goes back to the 20th century. The ideas and concepts began in the 1950s and 60s. The nanoscience and nanotechnology was started by physicist Richard Feynman. Feynman described that a process in which scientists would be able to manipulate and control individual atoms and molecules. So now we will be concentrating on the applications of nanomaterials and nanotechnology. So first we will look into the nanomedicine field. Nanomedicine is the medical application of nanotechnology. Nanomedicine ranges from medical applications of nanomaterials to nanoelectronic biosensors and even possible future applications of molecular nanotechnology. So now we will be seeing about how nanotechnology will be able to cure the cancer. It is called the molecular imaging and therapy. At first, the cancer is diagnosed by nanotechnology. Then, nanomaterials are injected into the targeted area or cells and tissues. Then, we are making a homing on tumor. Then, it follows that it kills the cancer cells. So it is a localized therapy where individual tissues and cells which are affected by tumor are cured by application of nanobots or nanomaterials. Nanotechnology also helps in improved imaging techniques. The next one is energy applications of nanotechnology. An important subfield of nanotechnology related to energy is nanofabrication. Nanofabrication is the process of designing and creating devices on the nanoscale. Creating devices smaller than 100 nanometers opens many doors for the development of new ways to capture, store and transfer energy. Next one is nanotechnology in memory and storage. This is a 2 gigabyte hard drive which is shown in the figure. It weighs about 70 pounds. It was first used in the 1980s. Its cost at that time ranged from $80,000 to $140,000. Two gigabyte in 1980s cost around $80,000, whereas 2 gigabyte in 1990s cost around rupees 200 only. 2 gigabyte in 2010 costed around $5 only. The current research shows that by using nanotechnology, 1000 GB of memory can fit on the head of this pin. 1000 GB is 1 terabyte. Nanotechnologies for flexible electronics. It is also an application in flexible electronics. Nanomaterials are playing a vital role in the development of flexible electronics. Only by manipulating the nanoscale structure of materials can we create components with the necessary electronic properties which can also be made flexible. The next one is industrial applications of nanotechnology. Surfaces and coatings. Nanotechnology may be used to coat the surface with very fine filament of powder. The most prominent application of nanotechnology in the household is self-cleaning or easy-to-clean surfaces on ceramics or glasses. Nano-ceramic particles have improved the smoothness and heat resistance of common household equipment such as the flat iron. Then in textiles also nanotechnology have made inroads. The use of engineered nanofibers already makes clothes water and stain repellent or wrinkle free. Textiles with a nanotechnological finish can be washed less frequently and at lower temperatures. Nanotechnology has been used to integrate tiny carbon particles membrane and guarantee full surface protection from electrostatic charges for the wearer. In military also, nanotechnology found its use. By using nanotechnology, the military would be able to create sensor systems that could detect biological agents. Nanoparticles can be injected into the material on soldiers' uniforms to not only make the material more durable, but also to protect soldiers from many different dangers such as high temperatures, impacts and chemicals. Next, we will see the obstacles and hurdles which are facing the development of nanotechnology. Mass production or throughput and cost constraints are one of the major obstacles for the development of nanotechnology, and the funding requires long-term investments. Intellectual property issues, patent office that is overwhelmed and underqualified. So in conclusion, this topic I would like to say that nanotechnology is a brand new technology that has just begun. It is a revolutionary science that will change all what we know before. The future that we were watching just in science fiction movies will in the near future be real. This new technology will first of all keep us healthy because of robots that will repair every damage that we have in our body. Nanotechnology will give us an abundant energy because it will transform energy more effectively. Nanotechnology covers a lot of domains today and will cover a lot more in the near future. It is infinitely big and will make a lot of inventions come true, like teleportation, for example, which scientists are working on today. So these are the references which I have offered for preparing this PPT, and next I will be going in depth into nanotechnology. So we will be considering the topics of the day, that is current use of nanotechnology. So we will be introduced to nanotechnology, definition, history, timeline, tools and techniques such as carbon nanotubes, nanorods, nanoboards, approaches used such as top-down and bottom-up, materials used and applications such as drugs, fabrics, mobiles, electronics, computers and other uses, etc. A nanometer is a unit of length in the metric system equal to 1 billionth of a meter. Technology is the making, usage and knowledge of tools, machines and techniques in order to solve a problem or perform a specific function. So nanotechnology can be defined as the study of manipulating matter on an atomic scale. It refers to constructing and engineering of the functional systems at very micro level, or we can say at atomic level. As said above, Dr. Richard Feynman was the founder of nanotechnology. So invention of the scanning tunneling microscope in 1981 and the discovery of fullerene in 1985 led to the emergence of nanotechnology. The term nanotechnology had been coined by Norio Taniguchi in 1974. The early 2000s also saw the beginnings of commercial applications of nanotechnology, although these were limited to bulk application of nanomaterials. Silver nano platform for using silver nanoparticles as an antibacterial agent nanoparticle based transparent sunscreens, and carbon nanotubes for stain resistant textiles. So in macro we see a human being 6 feet tall, which is 2 billion nanometers. Apple is 80 million nanometer, an ant is 5 million nanometer. In the micro level, we see the diameter of a human hair, which is about 75,000 nanometer. The smallest the eye can see is 10,000 nanometer. And in very small scale, we can see the buckyball, which is 1 nanometer, DNA 2 nanometer, and diameter of a carbon nanotube is 1.3 nanometer. So the timeline can be defined as follows. Passive nanostructures are the first generation products. Dispersed nanostructures, aerosols, colloids, products incorporating nanostructures, coatings and nanoparticles, reinforced composites, nanostructured metals, polymers, ceramics, etc. The second phase started in the 2000s. It involved active nanostructures such as bioactive health effects. Example include targeted drugs, biodevices, and physico-chemical active. Example include 3D transistors, amplifiers, actuators, adaptive structures, etc. In 2005, we saw the development of nanosystems. Example is guided assembling, 3D networking, and new hierarchical architectures, robotics, evolutionary, etc. In 2010, we saw the molecular nanosystems, which is molecular devices by design, atomic design, and the emerging functions. The next one is tools and technology. There are several important modern developments: the atomic force microscope, the scanning tunneling microscope, or scanning probes that launched in nanotechnology. Various techniques of nanolithography such as optical lithography, X-ray lithography, dip pen nanolithography, electron beam lithography were also developed. Lithography in MEMS context is typically the transfer of a pattern into a photosensitive material by selective exposure to a radiation source such as light. The next one is carbon nanotube. We will be dealing with carbon nanotube. Carbon nanotubes are allotropes of carbon with a cylindrical nanostructure. They have length to diameter ratio of up to 1,32,000 to 0.1. Nanotubes are members of the fullerene structural family. Their name is derived from their long hollow structure with the walls formed by one atom thick sheets of carbon called graphene. Properties: highest strength to weight ratio helps in creating lightweight spacecrafts. It can easily penetrate membranes such as cell walls. It helps in cancer treatment. Electrical resistance changes significantly when other molecules attach themselves to the carbon atoms. It helps in developing sensors that can detect chemical vapors. Next one we will see is carbon nanotube. It is an application of nanotechnology. Eastern Bell Sports Incorporation is using CNT in making bicycle components. Zyvex Technology is using CNT for manufacturing of lightweight boards, replacing transistors from the silicon chips as they are small and emits less heat. In electric cables and wires also nanotechnology is used. In solar cells also carbon nanotube is used. In fabrics also carbon nanotubes is used. The next one is nanorods, otherwise called as quantum dots. Nanorods are one morphology of nanoscale objects. Dimensions typically range from 1 to 100 nanometer. They may be synthesized from metals or semiconducting materials. It's a combination of ligands act as self-control agents and bond to different facets of the nanorod with different strengths. This allows different phases of the nanorod to grow at different rates, producing an elongated object. So the uses of nanorods range from the display technologies because the reflectivity of the rods can be changed by changing their orientation with an applied electric field. In micro electromechanical systems such as MEMS, also nanorods are used. It is also used in cancer therapeutics. Nanobots are close to the scale of 10 power 9 minus 9. It is largely used in research and development phase. Nanobots of 1.5 nanometers across, capable of counting specific molecules in a chemical sample. Since nanorobots would be microscopic in size, it would probably be necessary for a very large number of them to work together to perform microscopic and macroscopic tasks. It is capable of replication using environmental resources. Next one is application. Detection of toxic components in the environment, in drug delivery and in biomedical instrumentation. So the next one is approaches in nanotechnology, that is how nanomaterials are developed. The first one approach is bottom-up approach. In the bottom-up approach, different materials and devices are constructed from molecular components of their own. They chemically assemble themselves by recognizing the molecules of their own breed. Examples of molecular self-assembly are Watson-Crick base pairing and nanolithography. The next approach is top-down approach. In top-down approach, nano objects and materials are created by larger entities without bouncing its atomic reactions. Usually, top-down approach is practiced less as compared to bottom-up approach. Solid-state techniques can also be used to create devices known as nano electromechanical systems or NEMS, which are related to micro electromechanical systems or MEMS. MEMS became practical once they could be fabricated using modified semiconductor device fabrication technologies normally used to make electronics. The materials used in nanotechnology are zinc oxide, which is dirt repellent, hydrophobic, and cosmetics and stain resistant. Silver ion has the property of healing the wounds. Aluminium silicate is a scratch resistance material. Gold ion is a chip fabrication and drug delivery. So application of nanotechnology includes a wide domain. It can be applied in energy, medicine, nano devices, optical engineering, defense and security, bioengineering, cosmetics and nanofabrics. Nanotechnology in drugs. It provides new options for drug delivery and drug therapies. It enables drugs to be delivered to precisely the right location in the body and release drug closes on a predetermined schedule for optimal treatment. It attaches the drug to a nano-sized carrier. The carrier becomes localized at the disease site, that is cancer tumor. Then they release medicine that kills the tumor. Current treatment is through radiotherapy or chemotherapy. Nanobots can clear the blockage in arteries. Next one is nanotechnology in fabrics. The properties of familiar materials are being changed by manufacturers who are adding nano-sized components to conventional materials to improve performance. For example, some clothing manufacturers are making water and stain repellent clothing using nano-sized whiskers in the fabric that cause water to bend up on the surface. In manufacturing bulletproof jackets also nanotechnology is used, making spill and dirt resistant antimicrobial and antibacterial fabrics. Nanotechnology in mobile. Morph, a nanotechnology concept device developed by Nokia Research Center and the University of Cambridge. The Morph will be super hydrophobic, making it extremely dirt repellent. It will be able to charge itself from available light sources using photovoltaic nanowire glass covering its surface. Nanoscale electronics also allows stretching. Nokia envisaged that as nanoscale mesa fibers will allow our mobile devices to be bent, stretched and folded into any number of conceivable shapes. Next one application is nanotechnology is used in electronics. Electrodes made from nanowires enable flat panel displays to be flexible as well as thinner than current flat panel displays. Nanolithography is used for fabrication of chips. The transistors are made of nanowires that are assembled on glass or thin films of flexible plastic. E-paper displays on sunglasses and map or car windshields. Nanotechnology also finds its use in computers. The silicon transistors in your computer may be replaced by transistors based on carbon nanotubes. A carbon nanotube is a molecule in form of hollow cylinder with a diameter of around a nanometer, which consists of pure carbon. Nanorods is an upcoming technology in the displace technique due to less consumption of electricity and less heat emission. Size of microprocessors are reduced to greater extent. Researchers at North Carolina State University says that growing arrays of magnetic nanoparticles called nanodots. Hewlett Packard is developing a memory device that uses nanowires coated with titanium oxide. One group of these nanowires is deposited parallel to another group. When a perpendicular nanowire is laid over a group of parallel wires, at each intersection a device called memory star is found. A memory star can be used as a single component memory cell in an integrated circuit. By reducing the diameter of the nanowires, researchers believe memory star memory chips can achieve high memory density than flash memory chips. Magnetic nanowires made of an alloy of iron and nickel are being used to create dense memory devices. Chips produced by Intel before I-series processors were between 65 nanometer and 45 nanometer. Later, with the help of nanotechnology, 22 nanometer chips were made, which itself is a milestone. Advantages of using carbon nanotubes: faster and smaller. Carbon nanotubes can be used to produce smaller and faster components. This will also result in computers that consume less energy. High speed and high capacity memory allows circuits to be more accurate on the atomic level. The other uses include cutting tools made of nanocrystalline materials such as tungsten carbide, tantalum carbide, and titanium carbide. They are more wear and erosion resistant and last longer than their conventional counterparts. Silver nanocrystals have been embedded in bandages to kill bacteria and prevent infection. Nanoparticulate-based synthetic bond formed by manipulating calcium and phosphate at the molecular level. Aerogel's lightest known solid, due to good insulating properties, is used in spacesuits and are proposed to be used in spacecrafts. In India, nanotechnology is used in IIT Mumbai. It is the premier organization in the field of nanotechnology. Research in the field of health, environment and medicines are still on. Starting in 2001, the Government of India launched the Nanoscience and Technology Initiative. Then in 2007, the Nanoscience and Technology Mission 2007 was initiated with an allocation of ₹1,000 crores for a period of 5 years. The main objectives of Nano Mission are basic research promotion, infrastructure development for carrying out front-tracking research, development of nanotechnologies and their applications, human resource development and international collaborations. So this figure displays the overall project, that is IIT Mumbai project on nanotechnology. So they are using silver and copper nanoparticles for water disinfection, carbon nanomaterials for sorption of heavy metals, etc. The possibilities for the future are nanotechnology may make it possible to manufacture lighter, stronger and programmable materials that require less energy to produce than conventional material, and that promise greater fuel efficiency in land transportation, ships, aircraft and space vehicles. The future of nanotechnology could very well include the use of nanorobotics. These nanorobots have the potential to take on human tasks as well as tasks that humans could never complete. The rebuilding of the depleted ozone layer could potentially be able to be performed. There would be an entire nanosurgical field to help cure everything from natural aging to diabetes to bone spurs. There would be almost nothing that couldn't be repaired with the introduction of nanosurgery. There are some pitfalls of nanotechnology. Nanoparticles can get into the body through the skin, lungs and digestive system, thus creating free radicals that can cause cell damage. Once nanoparticles are in the bloodstream, they will be able to cross the blood-brain barrier. The most dangerous nano application used for military purposes is the nanobomb that contain engineered self-multiplying deadly viruses that can continue to wipe out a community, country, or even a civilization. Nanobots, because of their replicating behavior, can be a big threat to grey goo. So the bottom line is that the next big thing is really small. And these are the references which I have used for nanotechnology presentation. Next, I will be presenting you about the nanomaterials. So it is similar to nanotechnology. The materials which were produced by using nanotechnology are called nanomaterials. The word nanotechnology was first used by Norio Tadeucci in 1974 to refer to precise and accurate tolerance required for machining and finishing of materials. In 1981, Drexler described a new bottom-up technique instead of top-down. The term nano devices comes from the Greek word for dwarf. A nanometer is a billionth of a meter. So we have already seen the scale of things. The materials having at least one dimension in nanometric scale are called nanomaterials. Nanotechnology is the understanding and control of matter at dimensions of roughly 1 to 100 nanometers, where unique phenomena enable novel applications. Encompassing nanoscale science, engineering, and technology, nanotechnology involves imaging, measuring, modeling, and manipulating matter at this length scale. The term is really an umbrella term that covers disciplines that have very old historic roots. So what is so special about nanotechnology is that first, it is incredibly broad, interdisciplinary field. It requires expertise in physics, chemistry, material science, biology, mechanical and electrical engineering, medicine and their collective knowledge. The boundary between atoms and molecules in the macro part. Particles having sizes in the range of 1 to 100 nanometer are termed as nanoparticles, and the applications of nano-sized particles is what we call nanotechnology. At the nanoscale, the physical, chemical and biological properties of materials differ in fundamental and valuable ways from the properties of individual atoms and molecules or bulk matter. With the reduction in size, the surface area of materials and surface energy increase tremendously. For example, the material having side of 0.77 cm has a total surface area of 3.6 cm squared, and the surface energy is 7.2 into 10 power minus 5 joules per gram. For a material having side as 0.01 cm, the total surface area will be around 280 cm squared, and the surface energy is 5.6 into 10 power minus 3 joule per gram. But for a material which is having 10 power minus 7 cm as its side, that is 1 nanometer, the total surface area would be around 2.8 into 10 power 7, and the surface energy would be around 560 joules per gram. Because in the nanomaterial, 90% of the atoms or molecules occupy the surfaces. Therefore, the surface energy is very large. Then we will be discussing about the types of nanostructures. Nanostructures are classified as nanoclusters, which is a zero-dimensional structure, nanotubes, fibers and rods, which is a one-dimensional structure, films and pores, which is a two-dimensional structure, polycrystals, which is a three-dimensional structure. So, as we have seen before, there are two approaches to nanomaterial synthesis. They are top-down and bottom-up approach. In top-down approach, you are segregating the particles from very large size to nanomaterial size, whereas in bottom-up approach, you are making the nano-sized particles to form clusters to make a gel, as it is used in sol gel processing, to make larger molecules, and the larger molecules cluster together to form larger cluster of molecules than an object itself. The next one is about top-down approach. Generally, a bulk material is taken, machined and modified to obtain required size and shape. The example of this approach is the production of integrated circuits by etching or lithography. For nanomaterial synthesis, ball milling is used. In the figure here, you can see the nanoparticles, that is size having 1 nanometer in diameter. Macrocrystalline structures are broken down into nanocrystalline structures as shown in figure B. In the bottom-up approach, it is used to build from basic material, for example, assembling materials from atom or molecules. The commonly used methods include solder processing, hydrothermal manufacturing, physical and chemical vapor deposition, and epitaxial growth. So, in top-down, we are segregating the bulk material into nanomaterials, whereas in bottom-up approach, the nanomaterials are clusters of atoms and molecules are joined together to form a bulk material. Then we will be discussing about the nature of nanomaterials. The nature is the best manufacturer of nanomaterials and nanostructures. By natural nanomaterial means the materials that belong to the natural world, that is plants, animal and mineral, without human modification or processing. Due to their structures, they have remarkable properties because of their inherent nanostructure. So you could see here the wings of butterflies are made of nanomaterials. The wings of peacock are made of nanomaterials. The reason behind the butterflies having different colors is that there are several layers of nanomaterials in the butterflies' wings which reflect the light at various layers, leading to the different color of their wings. Mimicking butterflies' colors is shown in the figure. Antibacterial properties of cicada wings is shown here. And mimicking of antibacterial properties of cicada wings is shown here. So, antibacterial properties means the nanomaterials are resistant to bacteria or they kill the bacteria. So, nanorods treated sample have more opposing towards the bacteria. So, a lotus leaf is a self-cleaning effect. An analysis of a lotus leaf is shown here. The hierarchical roughness structure is shown. So, hierarchical structure of gecko feet is shown here. The different structures of the different animals and their skin are shown here. Then nanomaterials in arts and cultural heritage. Stained glass windows. It is made of a composite of glass and nano-sized metal particles. The ruby red glasses often seen are a mixture of glass with ultra-fine gold powder. Nanomaterials in arts and cultural heritage. The liquor gas hub dating from the 5th century is an example for the nanomaterial. Due to the presence of nano-sized particles of silver, which is 66.2%, gold, which is 31.2%, and copper, which is 2.6%, up to 100 nanometer in size, that were embedded in the glass. Light absorption and scattering by these nanoparticles determines the different colors. Then application of nanomaterials. The important application is in paints. Incorporating nanoparticles in paints could improve their performance. It can impart various functional properties like self-cleaning. Then in sunscreens and cosmetics also nanomaterials are used. The traditional chemical UV protection approach suffers from its poor long-term stability. Nano-sized titanium dioxide and zinc oxide are currently used in some sunscreens as they absorb and reflect ultraviolet rays. Transparent to visible light and so are more appealing to the consumer. Nano-sized iron oxide is present in some lipsticks as a pigment. And next one is effluent treatment. Nano photocatalysts are much more efficient than micro and macro photocatalysts. They degrade the toxic colorants and other organic species. So in medicine, nanotechnology has been a boon in medical field by delivering drugs to specific cells using nanoparticles. The overall drug consumption and side effects can be lowered significantly by depositing the agent in the morbid region only and in no higher dose than needed. Then we will see in detail about the application of nanomaterials. In sensors, 4 gases, nanomaterials are used. Sensors employ their sensitivity to the changes in various parameters they are designed to measure. The measured parameters include electrical resistivity, chemical activity, magnetic permeability, thermal conductivity, and capacitance. A carbon monoxide sensor made of zirconium oxide uses its chemical stability to detect the presence of carbon monoxide. The oxygen atoms in zirconium oxide react with the carbon monoxide to partially reduce zirconium oxide. This reaction triggers a change in the sensor's characteristics, such as conductivity. The gases like nitrogen dioxide and nitrogen trihydrate can be detected on the basis of increase in electrical conductivity of nanomaterials. The next one is in food. Nanotechnology can be applied in the production, processing, safety and packaging of food. A nanocomposite coating process could improve food packaging by placing antimicrobial agents directly on the surface of the coated film. So in construction, nanotechnology has the potential to make construction faster, cheaper and safer. The silica is present in conventional concrete as part of the normal mix as silicon dioxide. When nanosilica is added to concrete, the particle packing can be improved to increase the mechanical properties. The nano-sized steel produces stronger steel cables which can be used in bridge construction. Nano titanium dioxide coated glass have properties of anti-fouling and glaze. So next one is in energy. Nanomaterials have the capacity to store huge amount of energy. Today's solar cells use multiple layers of different semiconductors in nanometric range. They are much more efficient than the 120 years before. Then the better insulation materials are available from the nanotechnology. Nanocrystalline materials synthesized by the soldier technique result in foam-like structures called aerogels. These aerogels are porous and extremely lightweight. Aerogels are composed of three-dimensional continuous networks of particles with the air trapped at their intersection. Tougher and hard cutting tools are another application of nanomaterials. Cutting tools made of nanocrystalline materials such as tungsten carbide, tantalum carbide and titanium carbide are much harder, much more wear resistant and erosion resistant. These tools are required for microelectronics. The next one is in high power magnets. The magnetic power depends on the specific surface area. The magnets made of nanocrystalline grains possess very unusual magnetic properties due to their extremely large surface area. They are used in ultra-sensitive analytical instruments and magnetic resonance imaging in medical diagnostics. They are also used in motors for ships. The next application is in enhanced performance of components. The fatigue strength is an important parameter that determines the component's life. The fatigue strength increases with the reduction in the grain size of the material. By using nanomaterials, the fatigue strength can be increased by an average of 200 to 300%. This flowchart shows the various applications of nanomaterials and the opportunity-driven influences and also the concern-driven influences of the nanomaterials. For example, the opportunity-driven influences for the applications of nanomaterials include increasing wealth, increasing population, new science and technology, increasing functionality, multifunctionality, miniaturization. The concern-driven influences on the applications of nanomaterials include the environment, safety, health and liability, national security, market forces and competition, energy, water and food, and the individual. The primary driving force for nanomaterial synthesis is the market need, and based upon these two driven influences, new or changed materials and processes are developed, and they are then developed into a new or adapted product. That's all about nanomaterials and nanosynthesis and nanomaterials and nanotechnology. Thank you for giving me an opportunity to present this material for you. I am very glad for presenting this material. Thank you once again.